Hello everyone, welcome back to the MCAT grind. Today we have General Chemistry, Chapter 1, the atomic structure. The periodic table will be given on the MCAT, so that makes things a lot easier, but you will need to know how to use it. When you see an atom, it will show the atomic symbol, which is Li for lithium if you locate it on the left side, and you should see two numbers. One should be the smaller one, referring to which number of atom it is, the atomic number, as well as a slightly larger number, most of the time a little bit more than double, and that's the atomic mass. What the atomic number denotes is the number of protons it has, and for a neutral atom, that means its state on the periodic table, it has the same number of electrons as well. Same number of protons, same number of electrons for the atomic mass. So for lithium, it would be 3 protons, as well as 3 electrons. For atomic mass, it is the number of protons plus the number of neutrons. And if we recall from grade 5, maybe grade 4 science, protons and neutrons are found in the nucleus, while the electrons are outside in orbits. The atomic weight is the weighted average of isotopes. Within each atom, there are several natural occurring isotopes, meaning that some may have more neutrons than others. Lithium, you notice how it's 6.9, and you can't really cut away part of a neutron. That's because some lithium exists naturally with 3 protons and 3 neutrons, and some others, the majority, exist with 3 protons and 4 neutrons. So atomic weight is a weighted average of all the proportions and the mass of the isotopes. Next, we have this diagram showing our neutrons and protons in the center and electrons outside in the shells. The shells denote where they are most likely found in a discrete amounts. So shell number 1 and shell number 2. The first shell can hold up to 2 electrons, and the second shell can hold up to 8 electrons. Now, how do we know how many electrons each shell hold? Using this, shells can hold 2 n squared electrons each. So let's say for n equals 4, shell number, it can hold 4 squared, that's 16 times 2, it can hold up to 32 electrons in total in that shell. How does it do that? Well, in each shell, there are also subshells. So for shell number, it can have 1, 2, 3, and so on. The number of subshell for each given shell is equals to 0 and blah 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 until n minus 1. So if we have an n shell of 1, the L for the subshell number is 0 up to n minus 1 up to 0, so it only has 1 shell and no subshells. For 2, if we have a shell number of 2, it can have 0, shell number 0, shell number 1, and that's it. It cannot have more than that, because up to 2 minus 1. So up to 0 and 1 subshells. Okay? And so forth. What we have here for the subshells are the specific notations. We have S, P, D, and F orbitals. Subshell orbitals. While electrons don't follow a continuous pathway, they're kind of sporadic. They are not like nice and even rotations in orbit. They generally follow within their own shells. So we have the S, P, D, and F orbitals, where we can most likely find the electrons. The S orbital denotes the S subshell orbital denotes to L equals 0, So you can notice how n equals 1 only has the s subshell, whereas if you have a 2 shell number, you have 0 subshell as well as the 1. So that's the p subshell orbital also. Now the D and the F go up to much higher as well, and you can hold more electrons. In total, we have SPDF, and it will be shown on the periodic table coming later. What we can do is then use these notations to identify the atom. For lithium, it has 1 s2 and 2 s1 because 2 electrons are found in the first shell and 1 electron is found in the second shell. And for carbon, we can denote the same, 1 in a first s2 and 2 electrons in a s subshell orbital of the second shell number, as well as there's also a p subshell, so it holds 2 electrons in that orbital too. Notice how p has a lot more empty orbitals that it can fill up, and of course subsequently you can fill it up with more electrons in the atom. Now notice here, when we have subshells, or when we have shells in general, n equals 1, n equals 2, n equals 3, the higher the electron go in the shells, the more energy that electron carries. Reason being is just when electron wants to jump from one shell to another, you need to be generating fast enough or getting enough energy to actually jump. So you can think about it, electron needs to absorb a certain amount of energy before it jumps high, and if it wants to get down, it will need to release some energy in a discrete amount. You can't just give it energy to make it halfway in between. You need just the right amount of energy to hit that orbital. Otherwise, the energy just won't be accepted. So, when electron jumping from lower orbital to higher shell, it will gain energy, and if it's going from higher orbital to lower, it will emit energy. Now we have several equations to go over. We have energy equals HF, which is Planck's constant H, 6.3 times 10 to the negative 34 joule a second, times F, which is just frequency. If we recall from earlier physics, we know that F equals c, which is the speed of light, divided by wavelength. So this is like the common Planck's equation we know, and that's the energy of photon. We also can use Bohr's model of energy of electron, which is RH over n squared. RH is an experimentally determined amount of energy per electron, 2.2 times 10 to the negative 18 joules per electron, divided by the number of that shell number squared. That's the energy of electron in that shell. So if I have energy of electron in number 1, in shell number 1, that is RH, negative RH divided by 1 squared, so that's negative 2.2 times 10 to the negative 18 joules. That's its potential. If we have shell in shell number 2, so that's over 4, that becomes 5 times 10 to the negative 19 joules, but that's negative, so that's closer to 0, so that's higher energy than the first shell. And when we're talking about potential, it matters because we want to find differences in their energy. We have combined the energy of photon to energy of electron to see what happens, or can we calculate the exact number of energy or the wavelength of photon that can generate that jump. So for the equation, we have 1 over ni, which is the initial shell it comes from, minus the 1 over n final, the final shell that it will jump to. This overall equation gives us the exact discrete amount of energy, and we can also relate that to discrete amount of wavelength that it will absorb. Why does this matter? Well, because we notice that any shell that jumps from the n1 shell, right? 1 over 1 is 1, minus whichever number here, it's going to be a lot bigger, and that results in a lot smaller wavelength. Now, smaller wavelength equals larger frequency. That means everything that jumps from the n shell equals 1 will have high frequency, and we can say that's in the UV light range. So we have determined that to be what's called a Lyman series. We don't need to exactly call that in an MCAT, but I think MCAT will, I've seen there's a couple questions asking the differences between jumping from 1 versus jumping from 2. So just note that there's a huge difference. There is a big difference in like the frequency change. So from 2, it's called the Balmer series, and that energy is noticeably a lot smaller compared to jumping from 1. And the wavelength will be bigger, and the frequency will be smaller, and that will be within the visible light spectrum range. So what I'm talking about is by shining UV light onto n equals 1, you can permit a change in jumping of the shells. And if you shine like a visible light onto n equals 2 electron, it could jump out of that shell. Finally, we have what's called Hund's rule. Hund's rule means that each subshell will need to be filled with electron first. Think about a movie theater. Most people will want to get their own seats instead of sitting close to another, so they want to fill up all the seats before getting close together. Off-ball principle basically follows that the lower energy ones will get filled up first. Think of all the movie theater again, and think of all the reclining seats. The ones are very nice and you can relax on. Soft, like lower energy, you can exert less energy on. You want to fill those up first before you go into like a rigid seat. So that's all for atomic structure. Yeah, we also have, I did not go over orbital number and spin number. Orbital number would just be subshell number from negative to positive, and spin number is just two numbers, which is positive spin or down spin. Alright, that's it. See you next time.